Really? Sonny's PR for bench is 135? That's insane. All right, so welcome back, everybody. For this one, if we only had one small group that did this, we might be pretty chill on this. We're going to start in today. We are looking at all those groups. You did research on each of the individual groups, or a little bit of reading on it at least. We're going to begin with the alkali metals today. So, as we're going through these, some groups are obviously going to have, some of these groups of metals, rather, are going to have more people that did it, so we'll get more people to draw from. I will fill in blanks as needed. Please don't make me go through all your sheets and organize them so I know who to call on. Just volunteer information. Cool. All right. So as we get rolling with this, in our notes right off the bat, the alkali metals are where we're going to begin today. So as we go through here, the alkali metals, these are really easy to identify. They are group 1 of our periodic table. Now, without knowing anything about the particular metals, can you tell me anything about the elements in group 1 that you know right off the bat? They have one valence electron. Do they like to grab 7 more or ditch the 1?
Ditch the 1.
So they like to be positively charged, or cations. We know that right off the bat. As we continue on, these metals, in my opinion, are some of the most interesting. Just to hit a few of the characteristics that we're going to see about these guys, like a lot of metals, these are shiny, or what's a better word for it? They have lustrous, or they are lustrous rather. Okay, these are extremely lustrous. Now compared to others, if I wanted to cut a piece of metal, what would I need in your mind? A knife? A saw.
Maybe like a diamond saw.
Maybe a diamond saw and a grinding wheel, realistically, right? You might be able to do it with hand if you have a good enough saw. Check it out. The alkali metals are super neat because to be able to cut the alkali metals, a butter knife would do the trick. They are extremely soft metals. You could pinch it down. You wouldn't want to do it, but you could bite them off if you really wanted to. Okay, they are crazy soft. So as we deal with this, they also have a little bit of luster, but we'll talk about that. What's it called when we can roll them out into like a flat sheet? Or bend them? So ductile is one of them. This is like we roll it up into wires or stretch it out. I'm fine with that. What about flattening it and bending it? Malleability, or they're malleable. And there's one more property of metals. We're not going to write this on every single one of them. They conduct something. Electricity. Turns out they also conduct heat pretty well, which is a property of metal. Yeah, you're good. And I can talk, I talk loud anyway. Okay. Lustrous, ductile, malleable, and conductive. Cool. So no shock there. Now, as we look at these, again, they are crazy, crazy soft, but on the other side of it, they're super duper reactive. So I'm going to say extremely soft, and reactive. So these are the ones that we looked at the short video of, and it will happen with all of them. If I take it and I throw it in water, they light on fire and kind of explode a little bit. They are super soft, but they're also super reactive. Okay, as we look at these, couple little things. We're just going to hit on little pieces. Before I move on to specific alkali metals, do either of you guys have anything that you'd like me to add about these? And it's from memory, because I collected that just now, right? No is an okay answer in this situation, just so you're aware. Okay, so as we look at it, if we were to look at a periodic table, we're going to see that there are quite a few elements. There's 7 definitely, right? Because there's 7 periods. We are not going to count hydrogen, though, because hydrogen is not a metal. It just has its own unique place on the periodic table. So as we're looking at these, without looking, we're just going to check your atomic symbol knowledge. Li, what is it? It's lithium. What about
Sodium.
Okay.
Potassium.
Potassium. Okay, so these are 3 that show up. Now, these are, we're just going to make little comments about it. Lithium, sodium, potassium. Do we need sodium in our body?
Yes.
Definitely. It's how brain signals move. Sodium channels is what they're called. Do we need potassium?
Yes.
Definitely. It helps with a whole lot of different stuff. What about lithium?
Yes.
So it's a pretty safe bet to say yes. But it's weird when you think it, because when you think of lithium, where would you find it? Lithium-ion batteries is probably where your head goes. We have lithium in us as well. If you know of the illness or know somebody with it, there are mental illnesses that are pretty severe. Really, any mental illness I would argue is severe. But when you get like real big ones like bipolar disorder, where it's actually you go from being manic, super happy, to really, really, really depressed, that like in the real quick time, you get treated with it, right? If somebody is struggling with mental illness in the form of depression, there's a chance that they've been prescribed antidepressants, right? In severe cases, lithium and compounds made with lithium are what are prescribed to people. Okay, so with this, there are some side effects, obviously, with any sort of pharmaceuticals that you might take. There are, obviously, with lithium as well. We're just going to make a little comment here. Sodium and potassium are essential for brain function. We need them. Now, they show up not as pure sodium and pure potassium, but it shows up as sodium chloride and potassium chloride. They're salts is what we look at them. But they are essential in your bodies for brain function. If somebody drinks like way too much water way too fast, they get really sick. In fact, so sick that you could die. You can die of drinking too much water. It's called water intoxication. Now, water is good for you in small doses. If you drink too much water, all of the extra salt in your body gets flushed out. And when you don't have salt in your body, your nerves can't function. When your nerves can't function, kind of important things like your heart beating doesn't happen, your lungs expanding doesn't happen. You need these things. Okay, lithium. There are, I guarantee, more places for this. Lithium with antidepressants. Not all of them. In fact, very few of them will be lithium-based, but they do exist. Okay, other places, obviously, batteries. I guarantee lithium gets used a ton of spots. Okay, as we move further down, there are a few more, and we're going to talk about a bunch of random elements today. Okay, these ones are going to be a little bit harder. RB. Anybody know this one? You might know it if you're reading the book. Rubidium. Okay, rubidium is a group 1 or alkali metal. How about CS? I heard 3 different elements. Say yours? Okay, it is not Counter-Strike. What was yours? Calcium would be close if it were Ca. I like it that your head's in the right spot. And I heard one more over here. Cesium. Okay, we have cesium. And it drives me crazy because when I spell this, there's not many words that I do this with. But I spell it with the British spelling for some reason. And FR, still in Europe, francium. Okay, as we're dealing with these get a little bit more scary as we go through. So lithium, sodium, potassium, they're needed. They're scary on their own, but they don't show up on their own in our bodies. If we look at cesium, and I'm going to spell it like your book does. When I normally spell it, I put an A right there as well. Don't know why, that's just how I saw it the first time. Okay, so cesium or CS. This gets used in various places. Anybody have lights that turn on when it gets dark? Probably not here so much, but have you guys seen the lights in your yard that turn on once it gets dark? Now, they don't think and they don't have eyes to see when it gets dark, right? So they have some sort of solar panel that powers them, but if they turn on when it's dark, then they're turning on when there's no sun shining, right? Okay, and that's kind of a weird idea. Okay, cesium. The most common place that it gets used in is there must be some sort of sensor, and it turns out that cesium, due to its, we're not going to go like into the chemistry, but light sensors. So when your camera on your phone decides whether or not it's going to flash, there's a cesium compound in your phone making the ultimate choice. Now, it's not actually making a choice. It's reactions that occur with photons and light that hits it, but it's cesium that's responsible for that. Okay, the other two, rubidium. I'm actually not going to say anything about rubidium, but we will talk about francium and cesium a little bit more. And this is not to scare you, but both of these are super duper radioactive. Okay, now radioactivity, radioactive. Doesn't have to be scary. There is bad radiation and there's less bad radiation. Even the bad radiation, if it's a small enough amount, there's no main concern. Bananas have potassium in them, right? Yep. Bananas are a little tiny bit radioactive. Not enough to trigger a Geiger counter or anything like that you might hear the clicking if you watch old shows, but they are radioactive. So as we're looking at this, we have talked about radioactivity a little bit. Do we know what it actually is? Okay, so I'm just going to have a small little thing here. This isn't our super focus right now. But all this means is that the nucleus breaks down. Nucleus breaks down and releases energy. Now, what it breaks down to, typically it's other elements, but for our purposes today, we just care for the fact that it does break down, and it turns out sometimes that energy is bad for us. Okay, for this, just a fun little thing, I'm not going to write it down. Somebody's element, I don't remember who, you said there's less than this much on the planet. I think it was you. Do you remember how much and what it was? So astatine is really rare, 70 milligrams in our entire planet. Francium is also pretty rare, less than 30 grams in all of the Earth, which 30 grams is nothing. Okay, this is all 6 of the alkali metals. Extremely reactive, and we see some applications of most of them. Cool. All right, well, group 1 metals, the alkali, they're pretty cool. Equally cool is group 2, and gosh, here I am, I've just forgotten the name of them. What is group 2? Somebody from memory. Ooh, they're the alkaline earth metals. So we better hit those too. Alkaline earth metals. Now, the names are super similar. I wish I had a good way for separating the two, but the N, I guess. I don't know. One of them is alkali, that's group 1, and then we get the alkaline. Okay, so these ones, they're still shiny. They are still malleable. They're still ductile, but they are not very conductive. Okay, so I'm just going to make the comment, instead of writing all that, I'll say not conductive. Not in a meaningful amount anyway. Okay, anything else that you can tell me about the alkaline earth metals? So they are metals, and I know what you're getting at. What group is this, first of all? Okay, how many valence electrons does it have?
2.
Okay, do you think it likes to get rid of the 2, or does it like to get 6 more?
Get rid of them.
It gets rid of them. So it normally also becomes positively charged, right? If I lose 2 negatives, that's like adding 2. Any idea what group it might click with? So definitely non-metals, but is there a group that needs 2 electrons?
16.
Anything in group 16 will willingly and happily bond with this. Now, with that said, it's really easy to get rid of 1 electron, right? Is it a little bit harder to get rid of 2? And because it's a little bit harder to get rid of those 2 valence electrons, then it makes sense, I hope, that we would say slightly less reactive than group 1. Any objections to using capital G for group as a shorthand?
These are the horizontal, right? Or vertical?
Verticals. Yep. Okay. Now, of these, they like to stick with those things from group 16. So just a small example here, 16 or 17, and we'll look at this. We didn't do this for the first, but we are going to check it out. Some common situations. If I wanted to stick calcium with fluorine, turns out we need 2 fluorines. So calcium difluoride is how we would say this. That's not our focus right now, but this is an element that exists. That is a group 2 metal, an alkaline earth, sticking with something from group 17. How many electrons can something from group 17 take?
1.
And how many does calcium have to give? How many valence electrons in group 2?
2.
Does it make sense that I need 2 things that can take 1 electron then? Which, there it is, 2 fluorines and 1 calcium. They stick together. Okay, other common ones. Magnesium is another lovely alkaline earth metal. It likes to stick to oxygen. Based on nothing else, we don't need a table in front of us. How many electrons is our magnesium going to give up? 2, because it's still group 2. Without knowing the table in front of you, any idea how many valence electrons oxygen must have? 6, because those 2 and the 6 add up to 8. And we see that oxygen is in group 16 just by this. Okay, One more crazy one, and we will actually see this one. This is strontium chloride. Okay. Now, it's strontium dichloride if you want to be really specific with it. But for the same reason, chlorine can only take one electron. We need 2 chlorines to get the 2 electrons from a calcium. Okay. Looking at these. Less reactive, but they do still react. They will bond with stuff. So we're going to talk about a few of these. What is this element? Magnesium. Okay. When we use magnesium, I'm just going to make really short comments. Do you want me to write the word magnesium as well? I don't want to. You can. Okay. For magnesium, couple little easy ways to apply this. First of all, it is a light and strong metal. And any recollection of what it gets used for, group 2 people? Cars make sense. Anything else? Cars, planes, space type stuff, definitely. All of those places show up. Now, other places. Anybody in here from time to time eat something other than meat and dairy? And it's probably going to be what? Vegetables and fruit, I would hope. Okay. Turns out plants are kind of weird in general. I eat food to get my energy. How do plants get their energy? From the sun. There's a whole name for this process. Photosynthesis. We're going to dig into your biological knowledge here. What in plants lets it turn the sunlight into energy? Holy cow, I was not expecting you to find it. Okay, chlorophyll. Turns out magnesium is essential for the chlorophyll that you will find in plants that produce energy. Chlorophyll, and then I'm just going to put this in parentheses, photosynthesis. Okay, we need magnesium. Plants need magnesium in order to photosynthesize. They get most of it out of the soil in various compounds. Cool. All right, others that are more common. What is Ca? When you hear calcium, what do you think of? Do you think of bones? I think of milk, but for the same reason, because calcium in milk makes strong bones. Okay, there are much better sources of calcium other than milk. Maybe, just maybe, the dairy industry had a reason to push this idea that everybody should be drinking milk all the time, because why? Yeah, right? If I can convince everybody to drink the super healthy milk, then they're going to buy the super healthy milk, and my wallet will be super healthy and full. Cool. All right, little conspiracy sprinkled in there. So as we're going through here, calcium, certainly common in milk. I'm okay with that. Milk and bones, but we're going to be more specific. This is common in a few different places. It is common in bones. It is also, and not super related, but we'll see it, limestone rock. Okay. Now, where I'm from, limestone is everywhere. We don't get limestone up here. But as we're looking at it, for this, just so we have it for future reference, we have calcium in limestone, comes out like this. This is what limestone's actual chemical formula is. What is limestone made of? Calcium, carbon, and oxygen. Okay, as we go through here, bones, this is called calcium carbonate. Not our main focus right now, but just kind of front loading a little bit. Alternatively, bones are still made of calcium, but our bones aren't made of rocks, I don't think. I've never checked my own personal bones, but I don't think they're rocks. Would you agree with that? Pretty sure they're not. But we still need calcium here. And it turns out that we take calcium and we stick it on with this, which calcium and what other elements do we have listed here? Not potassium. That's a K. Oxygen for sure. There's 4 oxygens. Anybody remember P? Starts with a F, which is phosphorus. Boom. Okay, so this is a phosphate, not our focus, but this is what is in bones. Other places. Have you guys ever heard the word chitin? Not kitten, chitin. C-H-I-T-I-N. Like, I know it's silly. Chitin. Okay. I have bones. Do fish have bones? Yes. Holy cow, does crabs have bones? They have shells, right? Now, their shells biologically seemingly should be made of something similar to our bones, right? Like it's what serves the same purpose. Chitin is a calcium compound that's found in shells of crustaceans and things like that. Okay, cool. Other places. Let's see. Others that are worth mentioning. And we're not doing all of them. We're going to look at BA. Anybody recall BA? Bear. That was close. That's beryllium. Barium is all that this one is. And I will write this one here because it's less common. Okay. Barium. This is less common, but it does still show up. It turns out that if we want to x-ray us, we use an x-ray machine, right? And if I wanted to know how much tissue damage I have, would an x-ray show that? Not typically, because x-rays pass through our skin and hit the plate behind it, but it doesn't pass through the bones completely, which is why we get that contrasting image when we shoot x-rays at these plates. If I wanted to check and see tissue damage without just cutting me open and looking, we would need a way to stop the x-rays from passing all the way through, but I don't want to have to cut myself open. Turns out barium can do this. If we take what is known as barium sulfate, and I'm just going to write out the formula here, and I want to notice phosphate was PO4. This is a sulfate instead, which we can start to see some maybe commonalities. This absorbs radiation, and specifically it absorbs X-rays. And the reason that we would want it to absorb X-rays, like our bones might do something similar, to check soft tissues.
Is this the material they use to use plates behind? Or
So it is not, this is something that you would put within somebody's body. You would inject them with it. It's a dye that you would have in there. Okay, we can x-ray and look at soft tissue if there's some barium sulfate flowing through it. Okay, nothing too crazy. That's groups 1 and 2. Give me another one. We have a whole big group here. Say it again. Transitions. Okay, this is going to be a big one. How many groups did transitions? I know you did and you did. You did the inners? Okay, cool. So, check this out. We're going to look at the transition metals. And these span multiple groups. You did the inners as well? Okay. So as we're looking at it, the transition metals, they're the wonky part of your periodic table. If we look at the table, and I'll throw it up here on the board. Which groups are the transition metals? 3 through 12. They're the smaller part of the table. Okay. So as we're dealing with this, we will just say groups 3 through 12. Now, we are obviously not going to list every element in each of the transition metal columns because not a chance we're going to write down like 60 elements. Not doing it. Okay. You can if you want to. I guarantee you can find applications of each and every single one of these. But let's run through a few of these. Now, all of them do some weird stuff, which we're not going to generalize those rules today, but they do some wonky stuff. Okay, specifically, lots of colorful things that we see. Any metal that's like crazy colored is probably a transition metal in some sense. Even non-crazy colored, steel, things like that, those are all transition elements. But it turns out that from time to time, we get little regions where we as human beings have found an exceptionally common use regardless of where we're from. The first of these is a triad known as the iron triad, which sounds kind of like it could be a cool band name. And we're going to pick this apart real quick. Iron, I know what iron is, at least in its basic sense. Triad.
3.
Groups of 3 are known as triads. So, it's not iron, iron, and iron, although that would make sense with the iron triad. We're just going to say, that, hey, this has the following 3. What is iron's symbol? Fe. Why? Cool. Iron. We get this one. So, ooh, I heard it. Check it out. I'm not going to the right screen. Okay. So, iron. Cobalt. What do you think the third of the triad might be? Look at you guys generalizing from the table. So we have iron, we have cobalt, and I'll just put the symbol here, CO, and we get nickel. Okay, Ni. Okay, the iron triad, as we're looking at it. Three metals that have similar properties and they get used in very, very similar spots. What do you think iron, cobalt to a lesser extent, and nickel? When you think of iron, I've used the same example over and over and over. Magnets are made of iron, so maybe I've used two examples over and over and over. Yeah. What is, not this building. If I want to build a skyscraper, am I going to build out of concrete? I might use some concrete, and I probably will use a lot of concrete realistically, but it's not all going to be concrete. Am I going to build out of wood? No, not a skyscraper. It's going to rot and fall down. What am I going to build it out of? Iron. Okay. Not pure iron, though. I'm going to make steel. And if I want to make steel, what do you think I might mix together? Just any gut feelings? Oh my, iron, cobalt, and nickel, and there's lots of different types of steel. This is steel. These are the main ingredients for steel and alloys. Now, all an alloy is when you mix two or more metals together, you get a new, different metal. All steel, rather, is an alloy of a few different pieces, but we use these three. Okay, nickel, it turns out, this is used to prevent your iron from rusting. Okay, so if you have, I don't know, can you guys think of any sort of steel that doesn't rust? Stainless steel probably has some what in it? Nickel, that would make sense. Okay, with these, only other thing they're going to make a comment on is that turns out that iron, is it common or rare to find iron in the ground? It's really common. There's a reason everything's made of iron. It is the second most abundant element in the crust. It's not going to be copper. Give me 1 second. I would put money on silicon. Or oxygen. Probably oxygen. Which seems weird because we think of oxygen as being a gas, but you stick it to silicon, 2 oxygens and 1 silicon, you have silicon dioxide, which is sand. Cool. There's a lot of dirt on our planet. Cool. All right. Now, other groups within the transition metals. We get these triads that show up, and there's a few of them, and they don't all get names. But I want to make some coins, and I'm just pretending here like I am going to start making my own coins, and we're going to take a time machine and say this hasn't been done before. What are my coins going to be made of? Copper? So you're thinking American nickels, I imagine. Nickel's hard to get. Go back like 500 years, or think of any race like the Olympics. Gold, silver, and bronze, which is just copper with other stuff. Okay, so as we look at it, turns out that if we want to make coins, those are pretty abundant and going to be used throughout all of history. We get what is known as the coinage triad. Okay, for our coinage triad, we get, again, 3 things, and we've already listed them. We have gold, we have silver, and what was that third one? Copper. Okay, as we go through here, just to check, what's gold? AU. Aurum. What's silver? AG for Ashley Go. And what about copper? How did you know that? That's a good point. Okay, my bad, I forgot that. Okay, we have these 3 that get used for coins. Why would they be used as coins, do you think? They're common, so that's one obvious choice. Why don't we use iron? Iron's really common to make, or for a metal. Why would I use these instead of... It rusts, it's cheap and common, so people could counterfeit it pretty easily. If I want to make coins, do I have to be able to, like, form them and melt them and stuff? So these are a little bit more malleable than things like iron. They're perfect for this. They're rare enough that people can't duplicate it easily, but they're also soft enough and malleable enough that I can bend them to my will. Okay, as we're looking at it, alternatively, very few things do this. These are found as free elements, which means there are places on the planet where you will find like nice, clean, pure gold, nice, clean, pure silver, nice, clean, pure copper. It is uncommon that you do the same with iron. Okay, we'll talk about how you get that stuff out of it. Cool. Any other important metals? Did anybody do this transition, or did we decide no? Anybody do the transition metals? Okay, so I'm just going to keep talking. One more triad, and I don't have a name for this triad. Should we make one up? Okay, this is not going to be our real stuff. Zinc, cadmium, and mercury. Zinc, cadmium, and mercury. And I'm trying to think of what I would even call these if I were to make a triad out of them. Okay, quick check, because we've been doing it. What's zinc? Not what is it literally. What's the symbol for zinc? Z, there's one more letter. That's a good thought, but it's ZN. Okay, we're going to take total shot in the dark. Cadmium? C makes sense. CD seems reasonable to me. So cadmium would also make, or CN would be okay, but CD is what we're going to use and what is used. And then the last one is mercury. Anybody remember it? H. HG.
Oh, I got that.
Cool. I don't know the exact etymology of this, but hydro, and I can't remember the G, but because it behaves like a liquid, like water, hydro. Okay. As we're looking at this, turns out these get used in a lot of places. Battery production, and I'm just going to say batteries in general, will typically have zinc or cadmium or mercury or all three. Mercury, you guys know of at least one other application of it, I think. So that's a different element. Any idea? So Sabrian hit one application of it in her presentation. They used to use it for hat making, which is a risky move. Anywhere else? How warm is it in here? Pretty warm, like uncomfortable. My guess is like 72 because I'm hot. I have no idea what it actually is. How do you check temperature? And in old school thermometers, they were dangerous because you used mercury. Not anymore. We do not use mercury in them anymore. I would just call, I don't know what I would call this triad. Suggestions? We're not going to stick with it, but batteries and thermometers. Batmometer? I have no idea what I would call this one. Okay, we're about to get crazy. We are now going to go a level deeper. We went group 1 with our alkali, group 2 alkali earth, and now we're in the transitions, but we've skipped over a big old group of them. The inner transitions. Baller. Okay, you guys, I saw at least a few people where there's a ton of information that you gave me regarding the inner transitions. As we look at them, and I think that this is where the picture, bless you, comes in. Yeah, the table we've already talked about, it looks kind of goofy because it has that transition cut out. If we didn't take the other ones out, this is what the table looks like. And now it's like obnoxiously long and very different height all throughout. These look much nicer if we just take them out. So the numbers aren't there. Out of memory, just recall, where would we find the inner transitions?
Groups 3 to 4, period 6 to 7.
So I'm going to add one little word. I'm going to say between groups 3 to 4, or 3 and 4 rather. So we just sneak them right in there. So it's not group 3, it's not group 4, but it's between them. And then as we look at this, rows 6 and 7. Rows, or give me another word for the row of our table. Period 6 and 7. Okay. Now, what does the fact that 6 and 7 as a period mean to us? What does that number indicate?
That's how many rings it has.
Good. How many orbitals, the rings, the energy levels that something has? Cool. What can you guys tell me about these? There's 2 flavors of inner transitions, and don't eat them, not real flavor.
Oh, the other ones are lanthanide.
So the first group of it, or the first row, 6, shows up after lanthanum, so we call them the lanthanides. Now, I would caution if you're going to be using, like if you guys use your phones and internet and stuff with homework, which I assume you do, periodic tables vary. Sometimes lanthanum will sneak in there, sometimes it doesn't, so be really careful. Okay, as we look at the lanthanides, they're after lanthanum. These things, do you remember any uses of them? And that's okay. Like, that's all off of memory. If we want to make movies, we need fancy lights, right? So big fancy lights. So I'm going to say studio lights. Some of the lanthanides can be used here to make like really bright lights. Okay. Other places, when we think about really bright light, anybody ever use a fancy electronic device that you plug into a wall, and then if you're not careful, you're going to sunburn your eyes because you're sticking metals together? Do you know what I'm talking about? Okay, I'm going to do it slower. Here I am. I have something plugged into the wall, and I have two pieces of metal. I want to stick them together. And if I do this, I'm going to burn my eyeballs. Lightning would also burn it. Welding. It's welding. What do people wear during welding to protect their faces? The face mask. Now, it's not just glass that's painted black, right? Because if you've ever looked through a welding mask, you can see through it. You just need really, really bright light. Turns out, lanthanides are what get used in there. So, it's used for glass that converts UV light, so ultraviolet light that burns us, whether it's your skin or your eyes, and it converts it into visible light. If you happen to be somewhere in your life and there's a solar eclipse, and you have access to welding glasses or goggles, mask, whatever, that's what you should use. Go stare at the sun. You're safe. It will not, like, the UV light will not get you. You can stare directly at the sun if you have a welding glass on.
Glass is blind if you don't, right?
Yeah, you will eventually. You could. Welding, like, I've seen people, my brother specifically, I remember vividly my brother doing welding, and he thought he was too cool for safety equipment, which is pretty common among young men. Nobody's too cool for safety equipment, just for the record. But he sunburned the crap out of his eyeballs, like literally to the point where his eyes peeled because he was too cool to do this. Nope, he can still see, but he doesn't have great vision. Okay, studio lights and UV protection.
How does that work?
What?
Why did solar eclipse blind you?
Because the sunlight blinds you. So, only for a very brief second. Like, if you look up at a solar eclipse and you time it in that one little spot where everything is completely covered, perfect. But if this is the sun and it's a ball of danger, right? So we'll just make this a big ball of danger here. So how long do you look at the sun for?
When I was younger, I used to do staring contests.
I know.
That is
That's pretty real.
interesting. Okay, you shouldn't. I guarantee you've done damage to your eyes, not irreparable, seemingly. But, okay, right now, you should not stare at this. Let's say that there's an eclipse. Should you stare at it right now? You could, right? You can always realistically look at the sun. But are you safe here?
No.
Why?
Because it's not fully eclipsed.
Yeah, look at this. All this light can still burn my eyes. Now, you would be safe
Yes.
here. Now, I'm not going to lie to you. Staring at the sun for 1 second or seconds, depending, I don't know how long your staring contests were, are not going to blind you instantly. But check it out. Do you get new eyes when they go bad? No. So if you do a bunch of damage when you're young, whether that damage you realize it or not, when might you recognize that damage is there? When you get older and you still can't go get a new set of eyeballs. I don't think that you're going to go blind from your... Did you win your contest against the sun? You beat the sun at a staring contest? I'm just messing with you. You may see negative effects later in life. I don't know. You're not going to go blind from it right now.
If you stare at the sun until the solar eclipse is full, you win.
I don't know if I agree with that. You win. Oh, no. Okay. So, beyond this, there are a bunch of them. We're not going to list them all. They're all crazy and wild. They're pretty rare because they're the inner transitions. Okay. Much cooler than the lanthanides are the actinides. And that's obviously an opinion, but I legitimately do think that the actinides are where it's at as far as interesting elements go. Group 1 and 2 are really interesting because of what they do with water. The actinides, they follow, is it actinium? Or is it actinum? It's actinium. Okay, so as we're looking at these, the actinides are one of these after actinium. And a couple things. These are all of them, radioactive. And when something is radioactive, it means that it is unstable. It likes to decay and spit off some energy because it has too much to handle. Okay, so with these, of the actinides that are all radioactive and unstable, only 2 of them are natural. And I'm going to preface this, we've never found them, to my knowledge, off of planet Earth, but 2 of them we find in Earth's crust, in rock and such, and all the others we make. They are synthetic. They are made in particle accelerators. They're likely and realistically are made in neutron stars, black holes, or supernova that are forming into black holes and so forth, but they're all scary. The only 2 that are natural are thorium, which if you've never heard of this might be the answer to energy on our planet. China has begun building thorium nuclear reactors. Thorium is radioactive, but it's much less dangerous than uranium. This could be the future. So thorium shows up naturally, and uranium is the only other actinide that shows up naturally. When we take uranium and refine it, which I think was Chelsea's, we make plutonium, which I think was Max, and they're both related to nuclear weapons because the amount of energy that they have within them, their instability or their radioactivity. Okay, I almost fell just now. All right, as we go, not fall, my foot almost slipped off. Okay, as we look at these, we get all of these metals. If I wanted to start a collection of these metals and I didn't have money to go buy them, or I couldn't buy them, where would I find all of these? In the ground. So if I start digging somewhere where there's uranium, am I going to find a big chunk of like glowing green radioactive rock? Probably not. Now, very few exist truly alone in nature. Gold we can find completely alone in nature, right? You can go pan for it or you can mine for it. But when we get stuff out of the ground, like if I want iron, do I just dig up a big chunk of steel? How do I dig it up? I mine it. So what do I mine? What do I actually carry out of the ground? I just carry out rocks. It's legitimately just rocks, but those rocks happen to have what in them? Some iron, and I am just going to stick with it. I like it. Okay, so check it out. Here's the very end of this section. Metals in nature. Because all the way up to 92, they do show up in nature. In nature, we are going to have a Minecraft discussion for a second. The rocks that you dig up, what are they called? And there's a lot of different types of rocks, but I could be wrong. I've never played Minecraft, so bear with me. They're minerals. Some rocks are classified as minerals. I'm cool with that. Resources. Have you guys heard the word ore? O-R-E. Yeah, absolutely. Yeah, absolutely. Okay, these, turns out, metals in nature show up mixed with other stuff. Now, I am literally just going to say other stuff, and it can be a few of them. Just because we didn't mention it here because we're talking about the metals. The other day we saw a video of some people in Indonesia making bank carrying big yellow rocks out of a volcano, right? So they really didn't make bank. They made $10 a day to carry those. But those big yellow rocks, they were big, pure bricks of sulfur. Mostly pure, at least. Most stuff, especially metals, do not show up with that. We have to dig them out of the ground. So, rather, they show up with other stuff, which when we have a metal mixed with other stuff, there's sometimes that we call it an ore. Okay. If I dig up a bunch of rocks and I say, check it out, I have some ore. Is that a true statement? It could be, right? Like, that's a weird question. Here's the weird thing. This word is not a real classification. If it is something that I can make money off of, like I'm going to refine it and get value out of the rock, I call it ore. If I dig it up and I'm not going to do anything with it, there's no value, it's just rock. That is a distinguishing factor. Can we make money out of it? Now, for a few of these, there's really common places. If you guys want, tomorrow I can show you a brief overview of how we go from iron, rocks, or rocks containing iron, and what it looks like and what it takes to turn those into steel, or at least pure iron. Like, we can do that. If you're not interested in that, I'm fine with it. We can do it quick. But there are some other pretty valuable places. Platinum is a very, very valuable metal. We didn't talk about it today. I mean, it's in here. It's in the transitions, but we didn't talk about it. Any idea where platinum that's in every single one of your phones comes from? So definitely the ground. Can you be so the ground on planet Earth? They sound like Australians when you hear them talk, but they're not Australians.
Oh, I was gonna say.
You're going to go to New Zealand. Okay. South Africa. South Africa is where like 90% of the world's, lost my train of thought, platinum comes from. Chromium. We didn't talk about it in here, but it turns out chromium gets used in really bright colors. Any guess where chromium comes from? Some of you come from there.
Canada.
The Philippines. Chromium in the Philippines. Okay, before you pack up or when you grab your phone, I do want you to take a quick picture of the following. You guys get the privilege of 17.1. You will find this on page 428, and I want you to do questions 1 through 5 tonight. Okay, before anybody leaves, if Lily's phone wound up with somebody else, you're all going to be counted as tardy if she doesn't get it, but she got it, so we're good. All right, homework. Here it is. 1 through 5, 17.1. Cool. Check my Twitter feed later. It'll be there. I'm lying. I don't have a Twitter. It's called X now. Peace out, A-Town.